All right, welcome back. We're continuing our journey through topological dynamics, following the incredible map laid out by Gordon Whyburn. Now, in our last few sessions, we got a handle on the basic ideas of spaces and sets. Today, we're going to give those spaces a brand new, powerful tool, a ruler.
But what kind of ruler are we talking about? Well, let's kick things off with a question that's going to really push your intuition to its limits. This isn't something you can just whip out a tape measure for, right? It shows us exactly why we need a much more powerful, more abstract blueprint for the whole idea of distance itself.
So, to answer a question like that, our everyday gut feelings just aren't going to cut it. We need to build the idea of distance from the ground up, from its most fundamental principles, its axioms. So yeah, let's dive right in.
At its core, a metric space is actually pretty simple. It's just a collection of things, any kind of things, and a function that tells us precisely how far apart any two of them are. We call this formal idea of distance a metric, and as you're about to see, it has to play by a very strict but really logical set of rules.
Okay, so think about it this way. If you had to invent the very idea of distance from scratch, what are the absolute non-negotiable rules your invention would have to follow? Well, Whyburn's text shows us there are three fundamental laws that any sensible idea of distance has to obey.
First up, and this one's kind of obvious, right? Distance can't be negative. You can't be -5 feet away from your desk. And the only way the distance between two things can be 0 is if they're the exact same thing, if you haven't moved at all. Makes perfect sense.
Second rule, it's got to be a two-way street. The distance from home to the store has to be the exact same as the distance from the store back home. The path is the same length no matter which direction you're going. It's totally symmetric.
And third, we've got the most important and famous rule of all, the triangle inequality. This is just the fancy mathematical way of saying that a direct path is always the shortest. Taking a detour through some other point y can never be a shortcut to get from x to z.
So here's the big takeaway. These three simple rules, that's the whole blueprint for distance. Anything, any function, no matter how weird it looks, if it follows these three rules, we can call it a valid distance metric. And what's so cool about that is it lets us start measuring things in all kinds of strange and wonderful new mathematical worlds.
Okay, so we've got our blueprint for distance. Now let's see what kind of worlds we can actually build with it. We'll start off somewhere familiar, and then, well, we're going to get a little weird.
First stop on our tour is a place you probably know and love, Euclidean space. This is just the world we learned about in geometry class. Points on a plane, points in 3D space. But we can generalize it to any number of dimensions, which we call En. And this formula, it should look pretty familiar, right? This is just the Pythagorean theorem, all dressed up for n dimensions. This is our standard everyday ruler, and you can bet it follows our three rules perfectly. All right, now let's jump into something way more out there, Hilbert space. In this world, a point isn't a location you can go to. It's an entire infinite sequence of numbers. Now this might sound super abstract, but Hilbert space is actually the foundation for things like quantum mechanics. It's the space we need to answer that question we started with.
And check this out. This is where the power of our rules, our axioms, really shines. The formula looks identical to the one for Euclidean space, but the context is totally different. Here, it's measuring the distance between two whole infinite sequences. That's the magic of abstract math right there.
Okay, but wait a second. It's easy enough to see that our regular old Euclidean distance is non-negative and symmetric. But how do we know for sure that it follows that trickiest rule of the triangle inequality? How can we be absolutely positive that this formula always guarantees a straight line as the shortest path?
All right, let's unpack this for a second, because proving our intuition is really what math is all about. The proof Whyburn gives us starts with a really clever algebraic trick, basically rewriting the distance from x to z by forcing it to take that detour through y. But the key move is applying this super powerful tool called the Cauchy-Schwarz inequality. In simple terms, it's a rule that puts a hard limit on how much two different sequences of numbers can line up with each other. By using it here, we prove, without a doubt, that our intuition was right all along. The direct path is always the shortest. Okay, so we've done all this work, we've carefully built this idea of a metric, we've stress-tested the rules. So what? What's the big deal? What's the payoff here for our study of topology?
The payoff is one word: precision. A metric gives us a concrete ruler. All those concepts that felt a little fuzzy before when we were just talking about open sets, now, with a ruler in our hand, they become sharp, measurable, and honestly, a lot easier to wrap your head around.
I mean, just look at the difference here. On the left, in general topology, defining a limit point is all about these abstract open sets. But on the right, in a metric space, it's crystal clear. It's saying a point P is a limit point if, for any tiny distance epsilon you can imagine, you can always find another point from the set that's even closer. That vague idea is replaced by a concrete measurement. That's the power a metric gives us.
And that brings us to our final thought for today. Now that we have a ruler, our whole toolbox has expanded. We're not just asking if sets are open or closed anymore. Now we can ask way cooler questions, like what's the diameter of a set? How far apart are two different sets? How does this whole idea of distance change how we think about things like connectedness? And that is exactly where we're headed next.